Hello, and welcome to part 2 of this tutorial series on pitch in Bitwig Studio. If you're new to Bitwig, or music production in general, I suggest watching part 1 first, where we cover basic key tracking and a few rules particular to Bitwig. If you're comfortable with Bitwig as a whole, but want to get into patching in the grid, you're in the right place. Let's get on with it, shall we? The first thing I should point out is that all the old rules still apply in the grid, so everything we've learned so far is still relevant. The filters in the grid all have key tracking built in by default, which is nice as it saves us having to mess around with the key track modulator. That even applies to the comb filter, so if you like comb filtering, save an FX Grid preset with the comb filter dragged in and use that instead of the puny device version. Anyhow, what's new? Well, number 1, our glorious central pitch, C3, has taken on even greater stature here in the grid. It's given the crown of 0. What on earth am I talking about? To explain that, first we have to remember that we're working in a modular environment here. As Bitwig themselves say, unless I just made this up myself, in the grid, all signals are born equal. By that, they mean that there's no differentiation in the grid between audio information, pitch information, frequency information, modulation information. All of it's represented by a dimensionless signal with a value between -1 and 1. Audible waves result from moving that signal very, very quickly, and most other information results from moving that signal rather more slowly. Each module in the grid translates that common signal into something more meaningful, like a frequency or a tempo, depending on the type of inlet you plug it into, and according to a standardized set of rules. Going back to pitch, that means that pitch in the grid is also represented by a value between -1 and 1. In other words, modules in the grid that have a pitch input all agree on a set of rules for how to translate that simple dimensionless value into a specific pitch, and the value right in the middle of -1 and 1, 0, is C3. Let's demonstrate that by dragging in a pitch module and using the value readout module to see what it says. Actually, let's also drag in an oscilloscope so you can see the pure untranslated signal. I suggest that anybody that wants to work in the grid gets very used to using these two modules. I use them in every single patch. They help me understand what I'm doing. The value readout module can be thought of as a translator. It translates our dimensionless -1 to 1 signal into real-world values. If we set it to hertz, for example, it translates the signal in a way that a pitch or frequency-based module would translate a signal received at its pitch input. If we set it to decibels, it tells us how a gain or level setting module would use the signal to set the volume of an audio signal. Okay, back to pitch again. Let's set up that simple noise patch we were using earlier, turn the filter up until it's resonating, turn off the key tracking on the filter so it stops tracking the pitch of the MIDI notes that we're sending into the grid, and let's feed it some manual pitches instead, using the static pitch module. First rule, any module with an orange pitch input will track pitch correctly if you set its pitch input to 120 semitones, which is the maximum allowed value. Note that my filter is no longer following the MIDI notes I'm playing, because I'm feeding it a static pitch now. Let's twiddle the pitch module a bit and hear the filter change the note at which it's resonating. Now let's swap out our static pitch module for a pitch sequence. Ignore the speed at which it's playing for now. I'll explain that in another video. Just concentrate on the pitches coming out of it. You can see on the value readout and the oscilloscope which pitches are being produced. C major again, but this time descending. How creative of me. If we want to go back to tracking the MIDI notes, it's as easy as changing our static pitch module out for the pitch in module. Here we've actually just replicated what happens under the hood when that orange key tracking icon is enabled for the grid oscillators, or when filters have their key tracking set to 100%. Let's add another value readout module and set it to numeric mode. Notice anything interesting? The values are jumping in discrete steps, and they range from 0 to 0.1. Remember that I'm playing a C major scale here, starting on C3 and ending on C4. So what does this tell us? It tells us that C3 in the grid is represented by the number 0, the central number, and it tells us that the note 1 octave above C3, i.e. C4, is represented by 0.1. Let's switch to another pitch sequence. This one is playing A minor, from A3 to A4. Look at the readouts again. It starts on 0.075 and it ends on 0.175. The numbers are different this time, but the space between two notes an octave apart is still 0.1. This is an important concept to get your head around in the grid. Because all signals are created equal, a numeric value can represent both a pitch and an interval. Sending a number into a pitch input will cause the module to translate that number into an absolute pitch, according to the rules of the grid, like we discussed before. Sending a 0 into an oscillator will tell it to play C3. Sending 0.2 into an oscillator will tell it to play C5. Sending 0.275 will tell it to play A5. However, in the grid, we can even add two pitches together. What does it mean to add a pitch to another pitch? Well, maybe I should be a bit clearer here. Remember how signals in the grid can represent different things in different contexts? When you add a pitch to a pitch in the grid, what you're really doing is adding an interval to a pitch. When dealing with pitch in the grid, every pitch also represents an interval in the context of pitch arithmetic. If you want to impress your friends, why don't you try multiplying two pitches together? Or even dividing them. Just kidding. If you're watching a video on pitch in Bitwig Studio, you don't have any friends. Anyhow, I can demonstrate this pitch versus interval concept with the constant module. Let's go back to our C3 to C4 pitch sequence, and I'll add some different numbers to it. Let's add 0.1 first. As you can see from the value readout, I just transposed that pitch sequence up by an octave. Let's try 0.025. I just transposed it by 3 semitones, a minor third. In practice, you probably won't need to remember any of these equivalences. Luckily, Bitwig provides pre-translated operations for you in the pitch section, transposition, octaver, etc. If I switch between my rudimentary maths and the transposition object here, you can see in here that they're doing exactly the same thing. Still, understanding the nature of this equivalence will help you get your head around modular patching much more quickly. To make this point really clear, I've set up several different sequences of modules in this example. All these modules are doing exactly the same thing, they just have different visual representations of the numeric operations that they're performing under the hood. In the top row, I'm using the static pitch object to generate my root pitch of D#2, and I'm adding 6 semitones to the signal using the add module, and the constant module set to 0.05, which, as we know, represents 6 semitones when functioning as an interval. In the second row, I've inverted this setup, so I'm using the constant module to generate the same root pitch of D#2, a numeric value of -0.075, and I'm adding 6 semitones to the signal using the add module and the static pitch module instead, set to F#3, which, as Bitwig tells us, represents an interval of 6 semitones in the context of this operation. In the third row, I'm using the value knob, which generates a value between 0 and 1, or between -1 and 1 when you set it to bipolar mode in the inspector. I've set it to -7.5%, as -7.5% of 1 equals -0.075. I'm then transposing this up 6 semitones using the transpose knob from the pitch section. These examples might seem a bit contrived in isolation, but trust me, once you start taking advantage of the, well, modular aspect of the grid, there's a whole world of unexpected melodic and harmonic treasure just waiting in there to be discovered. So that's it for part 2. As with anything in life, if this was all new to you, I suggest incorporating some of the ideas into your own music to help this information sink in. I'll fade this video out with a few patches exploiting the concepts we've covered. If you can figure out what they're doing, let me know in the comments. If you can't, don't worry, they're deliberately obtuse. Take it easy, and I'll see you next time.